I'm a PhD student in the School of Sport over here. Now we've got up here that we're looking at the contractile properties of muscle and retired rugby players. This is one of the things we'll be looking at. Now, if I just give you a little bit of a bit of an intro as to what we're doing with the project, so that the larger study, and then we can, you can fit the TMG or what we're doing with the TMG in that context. So, what we know is from rugby players, we know that they are, while they're playing and while they're active, we know that they have superior bone density to regular people, increased strength, more strength, and lean tissue mass. Now, what we don't know is what happens to these things, these properties, when they're retired. So when they get into older age, what the rugby player, the retired rugby player, what he looks like. So what we want to do is we want to look at these different things, and TMG is going to provide one of those, a measure of one of those properties for us. So with some of the things we're going to look at is, as well as the TMG, we're going to look at the bone density. So we're going to do a DEXA scan. So we're going to get that information of body composition, bone density, muscle mass, and fat mass. And also we're going to look at the various, there's different properties of the anatomy we're going to see. So we're going to take a look at the spine and to see if there's any abnormalities in the spine. Now, the TMG measurements we're going to do is I'm going to look at the rectus femoris and also the biceps femoris as well. So the idea with that is that the rectus femoris being a large sort of prime mover, and the biceps femoris being a antagonist to that. The way I've gone about it is we've used the work that Hannah's done and Ashley has done, insofar as they've come up with Ashley just briefly talked about it in his talk just then, is that he's come up with this sort of standard protocol for the probe placement. So that, you see, that's helped us insofar as with something like this, then it makes it a more repeatable kind of a thing that we can do. So the way we do it is, Ashley, what we do is we mark up we identify the greatest trochanter, the lateral condyle of the femur, and we go halfway between, and then we mark off the lateral borders of the muscle and go halfway between them as well. So we've got our kind of longitudinal and transverse spots to mark off, and that's where we place the probe. And then we place the electrodes 9 centimeters apart, so 4.5 centimeters away from the probe, superiorly and inferiorly. 9 centimeters being the distance we use because of Hannah's study there. We also look at the, like I said, the biceps femoris as well. Same thing there, we've got a standard protocol, and we go halfway between the ischial tuberosity and the lateral condyle of the femur again, and then again we mark off the lateral borders of the muscle and go halfway between there. So we've got our kind of standard method for where we place the probe. So we do this so we can repeat it, and then each time these participants come in, we get that. Now, what we're actually trying to get from this, so we've got to remember that this population, the rugby players, and the data, the TMG data certainly doesn't exist in this population right now. So we're hoping to get some idea of that. We also don't know, this is just the protocol that I've just talked about. What we also don't know is, as well as being ex-rugby players, they're also people. And so from that, we're going to get a spread of ages of these characteristics, of these properties. So we're going to get, and what we're hoping to do is, if we put together, you see, we'll get the DEXA information, which will give us our composition, if you like. We'll get the contractile properties. So effectively, what I'm interested in here is, how quick are these muscles twitching? So what is the contraction time for these big muscles? Because if I put that together with then something else that we're going to do, which I've not told you about, which is we're going to do a balance and posture assessment. We're then building up this picture of this older person and some of these sort of key bits of information. So how much muscle have they got? So how do they fare compared to our control group? What does the contraction time and the displacement, what is the properties of their muscle? And then if we put that together with the balance, what is their balance performance? together with these, and if there's any correlations with that. And not least as well, because they're an aging population, we'll have a range of ages of participant. We'll be able to see, I'm hoping to see if there's any correlation between, contraction time and age. So what I've done here is, one of the things that we've been able to see, it's not overly clear there because of the data things, it looks a lot clearer here, but when I'm collecting this data, you obviously see a characteristic curve of these muscles, and I think it's quite, it's probably something the TMG chaps will know a lot more about, but you do see these characteristic curves of the from the different muscles. So I can tell, the bicep femoris looks a lot different from the rectus femoris, and they do tend to be reproducible, so they're quite similar from one person to the next in terms of the shape of the curve, which I think is is something of interest. But the thing that one thing where there is a couple of questions on it, it's probably worth discussing with the chaps, is when obviously I'm going into this and we're doing I'm upping my current, so I start off at 20, go to 30, 40, 50, then I go up in fives, and then I tend to stop when we've got the peak, or we've got the we're not altering the displacement in the same way when we get up to the top sort of amplitudes, and I am having to go up to 100 milliamps on a fair few of these participants. But one thing that was that will be important when it comes to the analysis now, a lot of people talk about the peak, stopping at the peak displacement. The thing that I'm quite interested in is when we get to the peak, if you look at this, you can't really see it too well, but if you look, there's about 3 separate plots up here. Okay, a couple there. Now when we get to the top, and they're quite similar, should the thing that we're looking at be the overlap or the drop down?
Usually the drop down happens when the whole limb starts to move away from the sensor. So usually that means that if you would measure rectus femoris, like I said before, and you would try to prevent the movement, then it can happen and the leg will move away. So that would be where you will get the decrease in displacement, and from my point of view, that's not something you should look for. So especially also when you were pointing at the biceps femoris curve, I would not
use this one because that's the other muscle. No, so, sorry, I was meaning more kind of in terms of the amount of.
So I would suggest that you stop when you get the stable first peak.
Yeah.
Don't look for.
But the thing I suppose I mean is, shouldn't have pointed to that. That is the peak that we're looking at there, the first peak. But say we look at something a bit more straightforward with the rectus femoris. If you're looking and you're going to get, so you think, right, I'm there or thereabouts, I've got it's peaked. You do another one and you think, it's overlapped, or it's maybe come down a little bit, or you think it's come down a little bit. Great.
Yeah, so
but then you come to look at your data, what I was going to say, you come to look at your data and you realise that actually not, it's continued to increase.
Yeah, sure.
So where are we in that situation then?
Just continue, you do one more.
Yeah.
But the thing is, if you just increase by 5 milliampere steps, sometimes what can happen, that's why I said, maybe it's better to use 10, because sometimes if you go from, let's say, 50 to 55, nothing will happen. If you continue to 60, you will get again rise of displacement. And if you go to 70, again it will continue. Sometimes the 5 milliampere step is not big enough to actually
elicit a response, like a different
response. I would, if whenever you're in doubt, just do one more.
Yeah.
If it stays the same, you're there. If it continues to increase, just go as long.
I'm talking about absolute minimal here. So, for example, you might look and the displacement might be 10.01 millimeters at the peak, and then you look at your raw data and you thought it had dropped down, but it's like I said, the next one is 10.02 or something. So, in other words, you would consider that as an overlap rather than a.
So the thing is, if it's if you have a difference that if the displacement for the last 2 or 3 measurements, it's just changing. Maybe also sometimes it can go up and down by like 0.1 millimeter, that's nothing really.
Yeah.
So you don't have to go into, you know, the smallest change. So you need to set up a certain range that you can see.
Yeah, of course. Whether there's the variance at that top level.
Because, like we said, it's very precise.
Yeah.
So it's impossible to get, you know, the two completely exactly the same measurements, because, you know, slight change of, I don't know, if I lean on the table during the measurement, I will create, you know, some small movement of the massage bed. This can influence, you know, 0.1 millimeter of displacement. So
maybe not be so OCD about it.
No.
Yeah. That's fair enough, that. No, fine. Anyway, I mean, so we've not got actually any kind of firm information, but I suspect we'll, from my preliminary analysis, which I've not got up here, we may see some correlation between age and contraction times.
So we did, it's not published, but we did in, you know, it was just internal. We were playing with the results a little bit that we got, because we have, in our database, we have, you know, a lot of subjects from, you know, different sports, different age groups, and we were just trying to see, you know, what kind of differences, you know, the age group will bring, you know, male, female, of course, different sport. And yes, it is. As you age, the contraction time will prolong. Yeah. And also displacement will increase because, you know, the muscle will lose its stiffness.
Did you find a different outcome in that it was certain muscles that were affected rather than others? Yeah,
sure. And also we found the same thing when we measured extremely young people, so children. So the biggest range of change of muscle behavior we observed with biceps femoris muscle.
Right.
So when they were, you know, when you measure a child 8, 9, 10, they will all have really slow biceps femoris. As they begin to grow, you know, at 13, 14, then the properties begin to shift. And again, when you get older, again, the biceps femoris will probably get much more slower than, for example, the vastus medialis. So if you look at the vastus medialis, because this is the muscle that you use immediately when you begin to walk, and until the really old age. So it doesn't, so the range of change is not very big. In the beginning, let's say it will be 30, then it will go maybe to 20 something, and then again it will go to 30 something. But the biceps can go from 40 to 20 and then to 50. So different muscles.
I was asking that because I think from when I've had a cursory look at the numbers, the biceps femoris seem to be more affected than rectus femoris, and I didn't actually see much doing with rectus femoris in age, but with biceps femoris there was much more kind of, and I thought whether I was only speculating as to why that would have been, but right, that's good. Right, anyway, so now it's any questions, by the way, before we move on to Matt? No? Yes?
Very quickly, so, so retired rugby players, do you have kind of injury history from their playing career?
Yeah, what I should have said was altered slightly. What we do is the first part of the study, we actually get we do like a general health type question, and it's quite comprehensive, so we'll get a full history of their playing level and where they played at, how long they played, what position they played, and we will get history of injury, you know, how many occurrences of a particular injury, surgery, whether there was any surgery on the injuries, whether that injury caused them to retire, and obviously how long they've been retired and such like. We also will get a sort of like a lifetime history of the physical activity, as well as their current levels of physical activity. So that will be something we could put together, because you see that the injury history and the physical activity to go with the composition, to go with the balance, to go with the TMG will be, you know, a lot of information there together, and whether that pulls anything out. But that's, you can imagine with the, you know, the balance, because we're looking at one of the things we're interested is that we're interested in the concussion side of things and the concussion history as well. But you know, obviously, if they've had bad ankles, then their balance performance is going to be altered. So we're obviously going to have to look at that, like the musculoskeletal side of things, together with the neuromuscular performance, if you like, of these chaps. And so whether they see the TMG thing is an interesting addition to those, because whether there is any match up between how they perform balance, because obviously if you're getting older, you think about the bigger picture of they're getting older, and then they're going to be more likely to, depending on what the balance is doing, whether they're more likely to fall over, and then whether they're more likely to fall over, can they adjust their step with the quicker contraction time, and then not fall over, or if they fall over, then they're going to break something because the bone density is low or not. So that's where it's all coming from, kind of thing. Yeah. Here we go.